The orthogonality catastrophe problem is considered to be solved for 50 years already, and it has important consequences for many dynamic phenomena, including Kondo effect, X-ray spectroscopy, etc. And a typical process which leads to orthogonality catastrophe setup is a sudden excitation of an electron in atom by incident X-ray, as in X-ray absorption, and the incident photon kicks out electron from the core level, and if in the so-called hard X-ray limits, electron may leave atom or system and leave a core hole. Depending on actually on the parameters, it can be different situations. The hard X-ray limit is fully corresponds to Anderson orthogonality catastrophe formulation, when a localized core hole acts as heavy impurity, and this heavy impurity polarize vacuum by creating electron hole pairs, and those electron hole pairs scatter of the potential created by a core hole. As predicted by Anderson, the overlap integral between initial and final state in the system before a hole and after the hole, not after, and together with this hole, should decay, well, at least with the volume of the system volume. However, more interesting question is how it decays with time. And just to mention, in the limit, in the more soft X-ray, in the softer X-ray limit, when electron does not leave atom, does not leave system, it also interacts with Fermi C electrons and holes. And this situation is closer to what is called resonant inelastic or resonant soft X-ray scattering. And I will also briefly touch this subject if I will have time. And again, so the question which was raised after Anderson prediction is how the overlap integral before and after excitation decays with time. And in the standard approach introduced by Nazier and Diagrammatic in 1969, this approach is based on the two K approximation, on standard K approximations. Now they're more or less standard. So its impurity potential is considered to be short range and with finite cross section, and also what is considered as non-interacting Fermi C. So electrons is not considered to be interacting with each other. And Nazier and Diagrammatic considered the scattering scenario where a hole in the core creates potential, and electrons at the Fermi level, around the Fermi level, scatter off this potential. And this process can be visualized with the help of Feynman diagrams for self-energy of impurity or core hole. So I will use name core hole, sometimes impurity, so just it is the same right now for me. Since we consider for localized impurity, so for impurity with infinite mass, for a localized hole, the green function of hole does not contain dependence on momentum. And this actually leads to the fact that all diagrams for a whole green function can be presented in terms of products of single loop diagrams, independent single loop diagrams. And in this approximation, Nazier and Diagrammatic found that the overlap integral between initial and final state modulus squared has a parallel decay with exponent which is proportional to a scattering phase shift, and this is for short range potential, and it's obvious that gamma is finite if and only if the scattering potential has a finite cross-section. However, both approximations, both these key approximations are invalid, or maybe it's better to say highly inaccurate in metals or in any problem involving charged particles. Or it's indeed invalid, because first of all interactions in metals are of long-range Coulomb nature, and the Coulomb potential has an infinite cross-section. So if we will take bare Coulomb and substitute it here, then we will have a diverged answer. And to avoid these divergences, the only possibility is to take into account the screening effect of bare Coulomb potential. And to get the screening, we have to accept that electrons around the Fermi levels, all electrons in the system, they interact via the same long-range Coulomb interaction, which produces dynamic screening in the system. So actually, and then obvious question arises is how the orthogonality catastrophe scenario gets modified in a metallic system or in a Coulomb system, where a long-range nature of interaction between particles and effect of dynamic screenings cannot be ignored. I will organize my talk in the following way. I will discuss first three effects: effect of dynamic screening of long-range Coulomb potential. Then I consider effect of plasmons, recoil effects, or in other words, effect of finite impurity mass. And then if I will have a time, I will discuss the resonance and elastic X-ray scattering technique. We just recently, a few weeks ago, we laid down a groundwork on this subject in our frameworks, which allows to deal with RIGS and with studying collective excitation within the RIGS method in the full Coulomb case, which takes into account all the effects of dynamic screening, etc. So I start with formalism, with setting up the problem in a way how we want to solve it, which does not rely on that approximation, that's completely uncontrollable approximations. So one loop diagrams, which were considered initially, they based on Taylor series expansion in terms of scattering potential. And if you take into account integration and summation over all intermediate events, we can replace any single loop by equivalent bosonic propagator F, or let's call it phi. And then the green function for impurity can be obtained by summing for over all the possible topologies of diagrams like that, whereas phi, this is a bosonic line, and G0 is a bare propagator for hole. And in these diagrams, we immediately recognize a Flatiron diagrammatic technique. And if we compute the total fully dressed green function for Flatiron in this setup, then in the asymptotic of Green's function at long times, at times longer than inverse Fermi energy, we will have access to Z factor, which is nothing but the overlap integral squared for the initial and final status. Is exactly what we are looking for, and it will help us to answer the question which we raised. So the actual thing, that is the actual physics behind the value of f, it's nothing but the screened, dynamically screened interaction in a system. And the only question is in actual form of phi. Depending on parameters, we can consider phi in a higher order diagrammatic expansions. Or if, for example, we are interested in perturbative limit for a Coulomb parameter Rs, then f can be presented within the random phase approximation. And then in this limit, in the limit of perturbative values of Coulomb parameter Rs, both this Flatiron approach to the solution of problem and RPA approach for bosonic line becomes exact. And if we want to go for larger values of RS, we will need to take into account more topologically different classes of diagrams. It is known how to do that. And additional simplification, again, if we are dealing with a localized hole or localized impurity, then green function has no momentum dependence because it's infinite mass. And then it's easy to see that the exact answer for green function can be presented in this exponential form where we have to take integral over all variables of bosonic propagator phi. And so let me continue with actually considering that effects which I outlined before. First, it's even in the case of short-range potential, how the people deal with that, with this kind of problem. One may wonder actually to what extent the orthogonality catastrophe scenario is getting modified by dynamic screening effects in metallic system. And to answer this question, we consider two versions of bosonic propagator, and with and without screening. In the first situation, without screening, we consider a simple construction where it's like it's a first diagram here, but and for potential we take Yukawa potential. Actual form of potential, short-range potential, is absolutely irrelevant here. But and as a polarization operator, we just take a product of bare electronic green function. So this construct corresponds to non-interacting case. The Fermi C electrons do not interact, and the construct is terminated by a static Yukawa potential. To take into account the effect of screening, we replace polarization operator by bare polarization operator by total polarization operator, which satisfies the Dyson equation with full bare Coulomb potential. So this is total polarization operator, otherwise it's the same Yukawa potential. Actually, it's worth mentioning that, dealing with Yukawa potential in this construct is mathematically inconsistent, because Yukawa is already a solution of Dyson equation in a static limit. So if you say we take Yukawa potentials here, and then we use this polarization operator in any form, people actually sometimes use this construct to mimic effect of dynamic screening, because otherwise it's difficult. So, and this is the reason why we follow this. It's mathematically consistent because Yukawa is already a solution of Dyson equation. In this construct, this construct leads to multiple counting of bubble diagrams. So this is mathematically inconsistent. Anyway, since people use it, I would like to see actually the effect of dynamic screening here.
So wait, Igor, I'm sorry, because I'm sorry to say I got a little bit lost in the details. If we could go back to basics for 1 second. No, you can stay with that slide. So the way I understood it, the old Anderson orthogonality catastrophe result was a solution, or Di Dominici-Noziere was a solution to the problem of non-interacting electron gas in a fixed potential characterized by a S-wave channel scattering phase shift at the Fermi surface.
Yeah.
Right?
No, any potential.
Well, one step, fine. But look,
yeah.
the key result was a logarithmic decay with a coefficient which was determined by the scattering phase shift at the Fermi surface. I understand that they wrote down a nice integral equation, they could solve it for any, but the key point is that the orthogonality catastrophe exponent is controlled by the scattering phase shift at the Fermi surface.
Yeah.
So here, if I understand correctly, you're comparing two potentials, a static one
Yep.
and a dynamically.
So actually, what I'm doing here is I'm taking this first term in Navier de Dominicis construct, and so I take a polarization operator as it is, G0, and for VS, which is short-range potential, I use Yukawa here.
But I guess my question is, look, the bottom line is that one thing you're doing is presumably should map on to more or less what Noziere de Dominici's said, and that the blue line should be a straight line with a slope which is controlled by the scattering phase shift of the potential.
Yeah.
Okay.
No, it's
not
red one.
Right. Very good. Now, then the blue one, which has dynamic screening,
yeah.
I guess the first question is, does it lead in the end to a different static scattering phase shift at the Fermi level? Or are you saying that once I know what the scattering phase shift is, I still get a different orthogonality exponent?
What I'm trying to say here is that this construct, well, people normally use in calculation just static potential without construct, but sometimes they understand that it's important to take into account dynamic effect and to mimic dynamic effect. Sometimes people use a construct like that, which pi has a time dependence. So they.
But wait.
And
the bottom line is that you have a potential which is eventually characterized by a scattering phase shift at the Fermi surface. And is that straight line on the blue thing given by the Nozière-Dominicis result with the S-channel phase shift at the Fermi surface, which is different because you're
not exactly. Not exactly, because Nozière-Dominicis had only Vy, and they didn't try to mimic. So as I understood completely that using static potential is a bad idea, but as they wrote, and well, Nozière wrote in a 1971 paper with somebody else, actually not using static potential is a very bad approximation, but actually it's not worse and not taken into account interaction between electrons. So what I'm showing here, because Nozière-Dominicis used only static potential without this polarization loop insertion. So what I'm trying to show, the effect of screening inside.
That's exactly what they did.
Well, okay.
Not
okay.
use pi,
okay.
because if
okay.
no pi, no.
But they used Yukawa potential in a different paper. In that paper, they used just a constant potential. So what I'm showing here is the effect, is the difference of between results when you take into account polarization effect, when you take into account interaction between electrons and holes at the Fermi level.
But what I'm still not getting is the long-time asymptotics are controlled. In the old story, the long-time asymptotics were characterized by an exponent, which was controlled by a scattering phase shift.
Yes,
and
this
and a prefactor.
Yeah.
Are you saying here that the difference is in the slopes is because the scattering phase shift is affected by screening?
By screening.
Or are you saying that the whole structure is wrong and should be replaced by something else?
So what I'm saying, well, first of all, it's not exact construct which we will be dealing at the end of the day, because we will have full Coulomb interaction lines here. But right now, just I'm interested in the internal, and I see from this graph that despite this, even this short range potential, which terminates this construct, the effect of screening, so first of all, orthogonality catastrophe survives, and power law of decay survives in both cases, but effect of screening lead to serious weakening of the power decay. So in interaction between electrons at the Fermi level and taking into account of effect of dynamic screening leads to weakening of power law decay, but orthogonality catastrophe in this setup survives. That's what I'm saying.
Sorry, but does it also survive the finite whole mass?
Fine, well, I will come to that point.
If I may rephrase on the question, because I didn't get the answer either. So if you calculate the new scattering phase in presence of your screening,
well, it will be smaller. In the case of phase, it will be smaller.
And you use this to get the new exponent. Will you get the same as the blue or not?
Can I object
no.
to the statement new scattering phase? Because the electrons are interacting and there is no single particle scattering anymore.
No, there is. It's a Fermi liquid. There is exactly a single scattering of the quasi-particles.
Maybe you have to know how to kind of formulate the particle scattering when they're strongly coupled.
But this actually puts some additional thing. If you see the effect of scattering, they strongly suppress exponent, and which this actually allows to make the following conclusion. People normally expect that in a metallic Fermi liquid, residual interaction between quasi-particle is very weak. This actually shows that it's wrong, and we cannot ignore interaction between quasi-particles in the Fermi liquid metallic regime. That's second conclusion which can be made from this not exact yet consideration. As I saw, I use here Yukawa potential, which is mathematically incorrect, just to show the effect of internals of screening. And And this demonstrates two things. First, orthogonality catastrophe survive, but decay of power law of decay becomes weaker, and it demonstrates that you cannot ignore interaction between quasi-particles. So, and second, screening of Coulomb potential leads to collective gap plasmon excitation at small momenta. And plasmons are the solution of equation for dielectric function equal to 0, and because of that, the dynamically screened potential features a plasmon pole. And before going to rigorous calculations with a full Coulomb case, I would like to consider what's called the plasmon pole approximation. Actually, the idea is to construct the form for phi, which satisfies two simple conditions. In the static limit, it's zero frequency and small momenta, small compared to Thomas Fermi screening momentum. The potential should restore the Yukawa form. And the second, it's zero momentum and small frequency. The dielectric function should future is zero at plasma frequency. So it corresponds to this form. And taking these two conditions, these two forms together, we can easily combine simple form for phi, which we can use in this exponential form for equation, and compute z factor to see how overlap integral decays. And the result is presented here by a red line. So we see that the result within the plasmon pole approximation saturates state to a constant, which actually eliminates the orthogonality catastrophe. However, if we, in a proper treatment, if we take into account not only the gap plasmon modes, but also soft modes like electron hole pairs, and this can be done by what I presented in formalism and within RPA, the power law of decay survives. So this happens because actually the orthogonality catastrophe scenario is based on existence of soft modes with low energy, so like electron hole pairs. So, but anyway, it's at short times, the plasmon pole approximation gives a reasonable result. Otherwise, it becomes inadequate, but at short times it's reasonable. And now we are going to actually the full Coulomb case, the case of dynamically screened Coulomb potential, and now F phi does not contain any short range potential, only honest Coulomb potential with all its features. And we consider two effects. First, we consider infinite mass, and infinite mass we consider we compute using two approaches. First is Flatiron Diagrammatic Monte Carlo, it's by dots, and second, that's exponential formula. It's dashed curve. Results are identical, so it's just if somebody didn't get that formula, that's exact answer. If you deal with infinite mass, you don't need to do diagrammatic Monte Carlo, but you can for infinite mass. And the second, we considered several finite masses. And for finite mass case, because now lines are not getting independent because momentum, green function for Hall or impurity depends on momentum, we can use only diagrammatic Monte Carlo result. And the results are presented here. And we can see that the recoil effects, or effect of final mass, they essentially shrink the region of validity of orthogonality catastrophe. So in other words, the region where the power law of decay survives, and eventually they lead for elimination of orthogonality catastrophe for a light mass. And conclusions that can be made here, well, first, even in a Coulomb system, when you do proper calculations with long-range dynamically screened Coulomb potential, the orthogonality catastrophe retains its universal power law, but exponent gamma is very sensitive to screening effect. That was the first observation. Second observation, that for dynamically screened Coulomb potential, so if you compare actual Coulomb potential, dynamically screened, and Yukawa potential, which people sometimes use despite the fact that it's wrong, Gamma, in the case of proper calculation with dynamically screened Coulomb, is larger than with static Euclid potential. So we are talking about here not, if we are talking about infinite mass, it's not effect like a break-in orthogonality catastrophe. It still survives, but to do properly and to get accurate answer, you need to take interaction properly. So Yukawa will give you several times different, smaller decay exponent. And even for short-range potentials, screening very strongly depends. Screening strongly suppresses the power, the exponent, the decay exponent. This is more or less all I wanted to say about orthogonality catastrophe, so I have time for Riggs.
Well, basically, we're now getting into discussion time. There was a lot of discussion.
Because for 5 minutes, it was started later, so 5 minutes enough for me.
So about 5 minutes. If
Yeah.
that's,
So everything that I discussed before is actually first step in the research dedicated to studying properties of collective excitation within the resonant elastic X-ray scattering method. The goal of this research is to learn how to extract information about collective excitations from experimental data. And as I already said, we just very recently laid down the groundwork where we actually studied Coulomb plasma in a full Coulomb case with a dynamically screened long-range Coulomb interaction. And we studied in a very restrictive, in a rather restrictive limit, which allowed us to do to solve problems semi-analytically. So for certainty, we considered the case of KH for transitional metals. And in this situation, photon kicks out electron from deep 1s shell and promotes it into the p shell. And then this electron leaves the hole, and together p electron and s hole, they emit d shell excitation, electron hole pairs, during the lifetime of hole. Eventually, p electron repopulates hole, leaving excitation behind, and those excitations are the subject of study by Riggs. So the lowest order diagrams contributing to that process, again, I am saying that we dealt with Coulomb plasma, are presented here. Actually, we have here SP bubbles, and they interact with d shell electrons and holes, and this interaction results in screened, dynamically screened Coulomb potential U in the same way as in the case of orthogonality catastrophe. And this F and I indices stands for incoming and final and outgoing photons. And since we are considering, so the limit which we consider here, it's a short lifetime of core hole, which allows us to replace green function, fully dressed green function for S hole and P electron by just bare green functions. Second, it's a small transfer momenta Q, which is not small compared to Fermi, Thomas Fermi screening momentum, and third, perturbative values of errors. And in this case, we can solve this problem semi-analytically. Maybe some integral can be, if we want a little bit more accurate answer within this approach, we need to compute it numerically. But we considered first and second order processes in this, corresponding to emission of one plasmon, two plasmons, electron hole pairs, and a hybrid process where electron hole pair and a plasmon are getting excited together. And in this figure, I show electron hole continuum. It's a first order process, and plasmon peak. And this is a dispersion for plasmon determined by position of the plasmon peak. So this is an experimental-like picture, but this obtained theoretically in a full Coulomb case with dynamically screening Coulomb interaction. And the second picture shows the curve presenting the line shape of intensity. It's not total intensity of the process, but it's line shape, which actually this curve corresponds to delta function, but for case of two plasmon emission process. And we also considered process or hybrid process with electron hole pair plus plasmon, but I do not show it here for brevity. So, as I said already, this was considered in a rather restrictive limit, and simplification allowed us to do semi-analytical solution of the problem, and implied by considered limit, it should be eliminated. And first of all, Bayer-Green function, if you not consider a very short lifetime, Bayer-Green function for S-hole P electron, it should be replaced by fully dressed green function, which was done, for example, it can be done in the same way as we did it in the case of orthogonality catastrophe problem. The diagrammatic expression for cross-section should not be limited by only two lowest order processes, actually single excitation and two plasmon and hybrid process excitation. And we need to go beyond RPA in computing dynamic screened interaction U. We also want to add phonon and magnetic degrees of freedom in the same way as we considered phonons in metals. And this actually leads to developing universal diagrammatic Monte Carlo approach to accurately describe Rick's cross-section in Coulomb system, and the main goal is again is to study how to extract information about excitations from experimental data. That's it. Thank you.